Welcome to EPG Pathshala lectures on numerical methods. Today we are going to consider a module on systems of linear equations and solution of systems of linear equations by direct methods. Our learning objectives set for today are basics of linear systems of equations, existence and uniqueness of solutions, numerical methods for finding solutions, and basic Gauss elimination method. In the previous module, the concept of matrices, operations on matrices, vector spaces, linear independence and basis were discussed. Also elementary row operations and their use in finding the rank of a matrix was discussed. In this module, we will be discussing the basics of general system of linear equations, methods to find solutions of a system, and basic Gauss elimination method will be discussed. So, matrix representation of the system of linear equations. Consider the system of m linear equations in n unknowns. So, this is a11 x1 plus a12 x2 plus a1 n xn equal to b1 and so on and so forth. This system we have considered earlier. Such a system can be expressed in the matrix form like this, Ax equal to b, where A is your coefficient matrix given by this a11, a12, and these are the coefficients that we are talking about. So, this is your coefficient matrix. X bar is a vector of unknowns x1, x2, x3 whose values are to be found from by solving this system of equation, and b bar equal to b1, b2, b3, bm is the right hand side vector actually. So, this is what we are talking about. You can see that when you take product of A with x, I will get this expression, and that is equal to b1. That is what we are going to consider. Now, the solution of a system we are going to talk about, and that is the system Ax equal to b is completely represented by a matrix called augmented matrix. See, what is important is that we want the coefficients of the variables and the right hand side vector. So, this matrix along with b bar is called as augmented matrix, and this is m cross n plus 1 because one column we are increasing here. Given A and B bar, any vector x bar equal to x1, x2, x3, xn that satisfies the m equations of the system is called as a solution of the system. In general, this system may have no solution, a unique solution, or infinitely many solutions. We will take an example to show that there could be these three types of solutions possible for the linear system of equation. So, first example we are considering part A. Consider the system of three equations in two unknowns, that is 2x1 plus 3x2 equal to 5, 4x1 minus 2x2 equal to 2, and 3x1 plus 4x2 equal to 8, which can be expressed in the matrix form as 2 3 because the coefficients are 2 3, 4 minus 2 and 3 4. So, this is your coefficient matrix. Unknowns are x1 x2 and right hand side vector is given by 5, 2 and 8 here. So, the only vector that satisfies the first two equations in this system x, for example, if I take only two equations, this one and this one, then I will see that x1 equal to 1 and x2 equal to 1 will give me 2 plus 3 equal to 5 and 4 minus 2 equal to 2. So, therefore, 1 is the only equation which satisfies this equation, two equations. And if you look at the third equation, if I try to substitute this value in the third equation, then I will get 3 plus 4, that is 7, but that is not equal to 8, and therefore, we conclude that the given system has no solution here. B part, if we consider, now a system consisting of only first two equations of the system in part A, if you consider, then you can say that it has a unique solution, one as mentioned above. So, instead of considering three equations in the system, I consider only two equations. Then this system will have a unique solution which is given by 1, and your C part says consider the system of three equations in three unknowns. So, 2x1 plus x2 plus 4x3 equal to 9, x1 minus x2 plus 2x2 equal to 3, and 4 x 1 plus 2 x 2 plus 8 x 3 equal to 18. So, if I consider this, and it can be easily verified that if I take 4 minus 2 k comma 1 comma k, where k is any arbitrary real number, then this is going to work as a solution to the system. If you substitute these values here, I will be able to show that all these equations are satisfied. And now, because k is unknown, by changing values of k, I can generate infinitely many solutions to this particular system. So, thus before solving the linear equations, it is essential to know about the existence and uniqueness of the solution to the system. Otherwise, if there are infinitely many solutions, which solution we are trying to find out may not be clear, and therefore, we have to know the existence and uniqueness of this. In that connection, I am going to only state some of the results, will not prove the results here, but we will state some of the results, and these three important results are there. Theorem 1 says that let A x bar equal to B bar be a system of m linear equations in n unknowns as mentioned above. Then the system has a solution if and only if rank of augmented matrix A B bar is equal to rank of A. So, this is your m by n plus 1 matrix, this is your m by n matrix. So, if rank of that is same as rank of A, then and only then this system will have solution, have a solution. We are not saying unique solution. Theorem 2 says that let A x bar equal to B bar be a system of n linear equations in n unknowns, then rank of A equal to n if rank of A is equal to n. Now, here we are taking n linear equations in n unknowns and rank of A equal to n, that is A is non singular if and only if the system has a unique solution. So, if it has a unique solution, this has to be non singular, if it is non singular, it has to have a unique solution. Note that for any n cross n matrix A, the rank of A will be equal to n, then for any vector B bar in R n, rank of A B bar also will be equal to n, and therefore, by first theorem augmented matrix will have the same rank as the matrix A, and therefore, solution will be always there. Only part is unique solution, that part can be proved mathematically. Now, the theorem 3 says let A x bar equal to B bar be a system of n linear equations in n unknowns, and if the rank of A augmented B bar is equal to rank of A and both these ranks are equal, therefore, it will have a solution, and if it is less than n, then the system has infinitely many solutions. So, that means for existence of one solution, I need augmented matrix must have same rank as this. For existence of unique solution, I must have system should be of n linear equations in n unknowns, and matrix A should be non singular, that means rank should be n, and if you have got the same system and if rank is less than n, then the system will have infinitely many solutions. So, these three results gives you idea about the existence and uniqueness of the solution. Now, we consider the first example that we have considered, that we are revisiting here, and we will see the conclusions regarding the number of solutions of the three systems given in example 1 can be drawn without actually solving them using the theorems 1, 2 and 3. Now, if you see for system in 4A, your coefficient matrix is this and your augmented matrix is this, and if you try to compute the rank of this, it can be easily verified that rank of A is equal to 2, whereas rank of A augmented B is 3, and because the ranks are not matching, the system has no solution, which already we have seen earlier. In the second case, for the system in 4B, the system of two equations in two unknowns, and your coefficient matrix is this, which has a rank 2, because this is a non singular matrix, and hence by the theorem 2 the system has a unique solution. So, that also we have seen earlier, and in 4C the system is of three equations in three unknowns with A equal to this and A augmented B will be equal to this, and if you look at the rank of A is equal to rank of A augmented B, and that rank is 2, and since R1, R2, R3 denote the rows vectors of both the matrices, then R1, R2 are linearly independent, whereas R1, R2, R3 are linearly dependent, because 2 R1 plus 0 R2 minus R3 will be equal to 0. You can see that this is 2 1 4, this is double. So, therefore, these two rows are linearly dependent, and therefore, rank is 2, and which is less than 3, and therefore, this system has infinitely many solutions, as we have already seen earlier. So, these theorems will be helpful to us for determining whether the system has unique solution or infinitely many solutions or no solution at all. The system of n linear equations, now we will concentrate on system of n linear equations in n unknowns, and where matrix is non-singular. So, matrix has a rank n and B bar is any non-zero vector in R n. So, your theorem 2 assures you that this has a unique solution. Now, we will discuss numerical methods for finding or solving such a system. Now, we have got a unique solution. This unique solution is to be found by using numerical methods here. So, what kind of methods are available to us for solving such a system of equation? If we use matrix theory, then there is a simple way to do it. Since n cross n matrix A in the system A is non-singular, that is rank of A is equal to n, A inverse exists, and if A inverse into A equal to identity matrix of order n, and that is same as A into A inverse. So, if we take x bar equal to A inverse B bar and put it in the system here. So, A x bar will be equal to A into A inverse B bar. A inverse is identity matrix into B bar, and identity matrix into B bar is B bar itself, and therefore, this satisfies our system A x bar equal to B bar, and therefore, that can be regarded as a solution of the system 1. So, thus one way to find a solution to the system is to find A inverse and multiply it by the right hand side vector B bar. But this is this does not make our task easier, because finding out A inverse would be equally difficult as finding out solution to the system. Hence, it is desirable to devise some systematic methods to find the solution of the system 1. So, we are talking about various methods available for solving system of equations. These methods can be classified in two classes, one direct methods and another iterative methods. The direct method find a solution of x bar to the system in one go by converting the given system into an equivalent system for which finding solution is easy. So, what we do is we are considering a system of, and then convert it into another system which is equivalent. So, solution of both the system will be identical, and then solving the easier system will get the solution of this, and that is in one go we do, that is direct method. Whereas, iterative methods generate a sequence xk of approximations to the solution of x bar, and starting with some initial guess x 0 bar and use some iterative scheme. So, how to get from previous solution to the next solution, that will decide our iterative scheme, that will be decided by the iterative scheme. So, we will discuss some of the direct methods in this module. Now, there are a number of direct methods. We will be considering Gauss elimination and then Jacobi methods and all that we will be considering later on. Gauss Jordan method we will consider. So, we will consider here now the simple system of equations again. So, same thing as, so what are the simple systems of equations for us for which readily the solution is available. For example, if I take identity matrix here into x bar equal to b bar, then naturally solution of such a system is nothing but x bar equal to b bar, because identity matrix into x bar is x bar itself, and therefore, x bar equal to b bar is the solution of this system. If we have got an upper triangular matrix which was defined in the earlier module. So, x bar equal to b bar, where A is an upper triangular matrix. Upper triangular matrix means lower triangle, this below diagonal elements are 0 and above diagonal elements are non-zero. So, we get an upper triangular matrix like this. So, the system will look like this. So, I can get, since A is non-singular, the diagonal elements a I will not be equal to 0, because of non singularity that is guaranteed that this in the upper triangular form the diagonal elements will not be equal to 0 for all I equal to 1 to 3 up to n. This is a known result in mathematics. In fact, if you look at from the determinant's point of view, the determinant of this matrix will be given by the product of this diagonal elements, and since matrix is non singular and determinant has to be non-zero, and therefore, none of them can be 0 here. So, the last equation yields the values of x n equal to b n by a n, because I can find out this, I can divide by a n n and I can get this. If I substitute that value in the n minus 1th equation, then I will get a n minus 1 n minus 1 x n minus 1 a n minus 1 n into x n plus b n minus 1. We get what? X n minus 1 will be equal to b n minus 1. So, this I know, x n I have already computed. So, I can subtract it from here. So, b n into a n n, and then the whole thing I will be dividing it by a n minus 1 by n minus 1 will give me x n minus 1, and continue this process of backward substitution. We obtain the values of x n minus 2, x n minus 3, x 2 and x 1. So, thereby we get the solution of the system. So, thus for solving n linear equations in n unknowns, one way is to convert the original system either in one of the above forms. So, either you convert it into the system 1, that is I n cross n x bar equal to b bar, or you convert it into upper triangular system. So, if I can do that, then I can get the solution of the system easily. Now, what we are doing, how to convert this system into another form, and there also we will be getting elementary row operations into action. We have already defined what are the elementary row operations earlier. As you know that elementary row operations are nothing but we have got either you can interchange the rows of the matrix, you can multiply any row of a matrix by a scalar multiple, and you can add scalar multiple of any other row to any other row, and the whole thing will be these are all elementary row operations. So, we will be using this elementary row operations for converting these systems. So, we have already seen the system A x bar equal to b bar is completely represented by augmented matrix A b bar, and hence if an elementary row operation is performed on the augmented matrix, it is essentially performed on the system itself. So, it is easy to see that interchanging two rows of the augmented matrix leads to interchanging the order of the equation, two equations in fact in the system, and this does not change anything in the system, and therefore, the solutions will also remain same even if we interchange the rows of the augmented matrix. Then multiplying any row of the augmented matrix by constant k leads to multiplying left hand side and right hand side of the corresponding equation by k, and if I multiply both the sides by k, equation does not change, and therefore, solution remains again essentially the same. Similarly, if an ith equation in the system is replaced by sum of ith equation and the k times the jth equation, because jth equation is also satisfied. So, the sum of k times the jth equation, it can be easily verified that the vector x bar in R n is the solution of the original system if and only if is the solution of the new system also. And therefore, these elementary row operations are such that in any order I apply these elementary row operations in the augmented matrix, my system essentially remains the same, and such system I am going to call them as equivalent system. So, thus if the augmented matrix A B is converted to the matrix C D, that means another matrix C augmented with D bar, after application of the set of elementary row operations of the system A x bar equal to b bar and C x, then the systems A x bar equal to b bar and C x bar equal to d bar are essentially the equivalent system in the sense that they have the same solution. Also, as remarked in the previous module, it is clear that if the rank of A is equal to n, then rank of A augmented b will be also equal to rank of C augmented d is equal to rank of C, and that will be also equal to n. So, therefore, rank does not change, because you know that we have used elementary row operations for finding out rank also, and rank of the matrix does not change by application of the elementary row operation, and therefore, all these ranks are same. So, what is the now we are talking about direct methods for finding out this. So, most direct methods to find solution to the system A x bar equal to b bar use the set of elementary row operations to be performed on the augmented matrix A b bar, so that it can be converted to an equivalent upper triangular matrix C d bar. So, that the corresponding system C x bar d bar can be solved by process of back substitution. To get such an upper triangular matrix C d, we use the row operations representing the process of elimination as illustrated in the previous module. So, we will do that here. So, our first method, which is one of the direct methods, that is Gauss elimination, simple Gauss elimination method. So, consider the system of n linear equations in n unknowns, again we are considering that, where A is non-singular and b bar is right hand side any non-zero vector in R n, and the Gauss elimination method for solving such a system is essentially divided into two parts. Part 1 consists of elimination process, which converts the given system into upper triangular form, and part 2 consists of back substitution process, which computes the solution to the system. Okay. This process has n minus 1 steps. In the first step, first variable x 1 is eliminated from the equation 2 to n. In the second step, x 2 is eliminated from the equation 3 to n, and so on. In the kth step, x k is eliminated from the equation k plus 1 to n. Let a I j k denote the element in the I jth cell of the matrix A k, which is obtained from matrix A after kth step. So, there are n minus 1 steps involved in the method. After kth step, whatever matrix is converted, I am denoting it by A k. For notational consistency, we denote original matrix A as 0th step, because nothing has been done on it. So, A 0 and its elements as A I j 0. Also, let B k denote the right hand side vector, and B I k denote its ith component after the kth step, because when you are applying row operations on augmented matrix, B also changes. Thus, the kth step, the augmented matrix A k B k is obtained from the matrix A k minus 1 B k minus 1 as this. So, what we are doing is, this is the simple formula that we are using. So, A I j k equal to A I j k minus 1 minus A I k k minus 1 A k j k minus 1 and divided by A k k k minus 1. So, for I equal to k plus 1 to n and j equal to k to n, this is what we are trying to do. So, I equal to k plus 1 to n and j equal to k to n, and B I k will be given by B I k minus 1. So, that means you take previous entry, that means at the k minus 1 step, whatever value of B I that you take, minus A I k k minus 1 into B k k minus 1 into A k k k minus 1 for I equal to k plus 1 to n. All other elements of A k B k are same as that of A k minus 1 B k minus 1. Note that at the kth step, all the below diagonal elements in the kth column become 0. We will see that in our illustration later on, how this works. So, we will check that little later, and hence the above computations are equivalent to row operations. What row operations I am doing now here? See, I am doing this on all these elements here. So, my elementary row operation is R I k plus R I k equal to R I k minus 1 minus this. So, whole thing I am trying to do, and that will not change any first entries at all, and therefore, this can be regarded as elementary row operations on this type of row operation. So, I am taking a scalar multiple of kth row and subtracting it from ith row and replacing my ith row in the next iteration, next step, by this difference. So, matrix A k minus 1 B k minus 1, after n minus 1 step, the computed matrix A n minus 1 B n minus 1 is an upper triangular matrix. So, this is what we are getting here. After n minus 1 steps, the computed matrix A n minus 1 B n minus 1 and upper triangular matrix as desired. So, we will get an upper triangular matrix as desired. And then your back substitution process begins. So, this process computes the solution of the system A, again A n minus 1 in x equal to B n minus 1. So, that is the last system that we get, which is also the solution of the original system A x bar equal to B bar, because solution does not change. As discussed earlier, the components of the solution vector x bar are computed in the backward direction using the formula like this. So, x n bar x n we are finding out from the last equation, that is B n n minus 1 divided by A n n minus 1, and x I will be obtained by 1 upon A I minus 1 into B I minus 1 minus A I j I minus 1 x j equal to I plus 1 to n for I equal to n minus 1 and so on and so forth. So, when we are computing x I, we already know the values of x I plus 1, x I plus 2 up to x n, and therefore, we are substituting here, and then we are getting the value of x I. Since we are going in the backward direction, this is called as back substitution. Let us look at the manual implementation of Gauss elimination algorithm. Let us take this system of equations like this. 4 equations we are given. By Gauss elimination method, the augmented matrix of the system is given by this. So, 2 3 0 1, 2 3 0 1 and the right hand side vector, right hand side element 4, and similarly I get 3 0 and all that. So, this is my augmented matrix. Now, if I write this augmented matrix here, so in the step 1 I want to eliminate this. So, what I want to do is I want to eliminate all the x 1, I want to eliminate x 1 from all these equations. So, eliminating x 1 from all these equations reduces to converting these coefficients of x 1 in the remaining equations to be 0. It will remain non-zero here, and all other elements here will become 0, and that I have to do by taking row operations like this. So, what I am doing is 3 by 2. So, what is 3? 3 you are getting from here. So, this is your A 2 1 divided by A 1 1. So, that is what I am taking, and multiply the first row R 1 by that and subtract it from R 2. So, if I do that, if I subtract it from R 2, your first element will automatically become 0, because 2 3 0 1 4 and I am multiplying this by 3 by 2. So, second row multiplied by 3 by 2 will give me again this will be also equal to 2 actually, and then I will be subtracting that from here. So, I am multiplying this row by 3 by 2. So, when I multiply 3 by 2 I will get 3, and when I am subtracting this from here, this 3 and 3 will be cancelled, and that therefore, I will be getting 0 element in this here. So, you can see that similarly I am doing the same thing 0 by 2. So, first element of the third row by 2, first element of the fourth row by 2, this is what I am trying to do here, and I am subtracting, multiplying by R 1 here all of them, and R 2, R 3, R 4. When I subtract that, I will get all these 3 elements 0. So, I have already eliminated x 1 from all the remaining entries here. Then I will do step 2. Now, step 2 I am concentrating only on these elements and not on these elements, because whatever I do here 0 will remain 0, and therefore, what I am now trying to do is I am trying to consider R 3, because this is minus 9 by 2, I am taking adding here, plus I am doing. So, I am considering here minus 9 by 2. So, I am adding plus 2 by 9 into R 2. So, I am taking 2 by 9 into R 2, and then I will be getting, because this element is 1. So, 1 divided by this and subtract. So, therefore, plus 2 by 9 into R 2 I will get. Now, this entry here is 1 by 2. So, 1 by 2 divided by 9 by 2. So, I will be getting here 1 by 9 into R 2, and R 4 plus this will give me 0 element here. So, like that I will be doing. So, this elimination is done up to this, and all these elements are changed. You can see that these elements remain same in this also. This row remains same and only changes in the remaining elements, and these two elements become 0 here. And similarly, the third step, I have to eliminate only now this entries you have to check, and I have to make 0 here. So, in order to make 0 here, I will be multiplying it by 28 by 20, that is 7 by 5 into R 1, subtract it from R 4. Actually, this should be R 3 and 7 by 5 R 3. So, R 4 minus this. When I do that, I will be getting this entry 0. So, I will get now a new system, which is upper triangular system of equations. Once I get that, I can compute the x 4 as from the previous here. So, this is minus 24 5 into x 4 equal to this. So, x 4 will be equal to 24 by 5 divided by 24 by 5. So, that is what I will be getting. So, minus 1 I will be getting. X 3 will be equal to minus 8 by 9. So, why minus 8 by 9? Because here we have got 8 by 9, minus 8 by 9, and then you are subtracting the remaining part here, minus 28 by 9 into minus 1 into this. So, I will get 1. Similarly, I will calculate x 2 from that formula, and x 1 x 4 x 4 I have calculated, x 3 I have calculated, x 2 I am calculating, and x 1 I am calculating after that. So, this is the process of back substitution, that is what we get. So, this is what we have described in this module. So, what is the summary? In this module, the following points were discussed: the results on existence and uniqueness of the solution of the general system of m linear equations in m unknowns were discussed. Then the numerical methods for solving. So, what are the types of numerical methods available? There are direct methods and indirect methods we have considered, and then basic Gauss elimination method was discussed, and in details actually we have discussed that, and relevant illustration was also given. Thank you.